In this demo, we'll be presenting our work on proactive security compliance enforcement. But let's first have a brief review on our previous works in the context of ARC. In September 2015, we presented our first demo on retroactive auditing of cloud virtual infrastructures. In June 2016, we presented our demo on auditing Layer 3 network isolation based on Tenant Guard published in NDSS 2017. Last but not least, in December 2016, we presented our work on Layer 2 network isolation. In this video, we're going to present our new demo on proactive auditing. But let's first have a high-level overview of our contribution. Previously, we presented Tenant Guard as an efficient module that audits virtual Layer 3 isolation. However, Tenant Guard can only detect compliance breaches after the fact, which leaves the door open for the attacker to leverage the security breach to mount other attacks. In our current proposal, we leverage a control feedback loop based on previously generated Tenant Guard compliance reports to drive an evolutive approach that proactively prevents security compliance breaches. And it does that by continuously enforcing security compliance. Now let's delve into our demo. The demo has three main stages. At the first stage, we present the security policy and a possible attack scenario which might violate that policy. Then at the second stage, we show retroactive auditing which can only detect such breaches after the fact, leaving a large time window for the attacker to proceed and could not prevent irreversible damages. At the third stage, we show proactive auditing in action, intercepting and checking every cloud operation in near real time and blocking those that are predicted to violate compliance. The security policy we're aiming at in this demo is network isolation, one of the most important policies in a multi-tenant cloud environment. It involves segregation between virtual resources and virtual networks belonging to different tenants. At virtual layer 3, this can be expressed as virtual machines belonging to two different tenants, A and B, cannot communicate or not being reachable from each other. Now suppose a malicious user from tenant A has gained an unauthorized access to the victim's machine in tenant B and modifies its security group to security group B1, which is supposedly a less restricted security group. Therefore, the attacker will be able to publish a communicating channel from his own virtual machine to the victims, and these two VMs will be reachable from each other, which is a breach according to network isolation policy. Now let's consider our previous work, retroactive auditing. In this command line window, we assume an attacker has gained access to the console and identified the victim's VM and its attached security group no connection. Security group no connection implements the most restricted connectivity policy. The attacker has tried and succeeded to modify the security group for the running VM to a less restricted one, in this case default security group, which would enable him to establish a communication channel with the victim's machine. Running Tenant Guard would allow the detection of this communication path, but after the fact. We can also see the result of on-demand auditing in our ARC dashboard. After audit process, we see the violation has been detected, but it's been detected after the fact, which leaves a vulnerability window for the attacker to proceed. Now let's move on to the last stage where we present proactive auditing. As opposed to what we had before in retroactive auditing, proactive auditing module LeaPS for the same scenario would intercept and block any modifications to security groups which violate security policy network isolation. Therefore, no compliance breach will occur. Let's see proactive auditing in action. From our new ARC dashboard, we set proactive mode to on. We also need to specify some security properties. To do so, we select Custom Properties and select those properties of our interest. In this case, we choose Custom Properties, but we also have the option of choosing other properties such as CCM or ISO. We can specify standard, for example CCM, Domain can be infrastructure and virtualization, and property can be no downgrade of security group. Our users have also the option of specifying the proactive action to be imposed in case of a security property violation. It can be an operation denial or a simple warning. After that, we can also upload a configuration file to provide properties to our proactive module LeaPS. These properties include a threshold probability to trigger proactiveness for each security property, the relevant critical events, and the watchlist content in case of that critical event occurrence. For example, in the first line we can see no downgrade of security group as security property, its related critical event attached security group, threshold probability of 0.33, and the watchlist content is instance ID. After this, in the background, LeaPS starts an initialization phase where it collects log files and processes them to learn the dependency model. Here we're showing a learning engine. The dependency model is visualized as a graph. Then the probability of transitions between states are learned based on the process log sequence of events and the probability of their occurrence. Other configurations can also be defined in our Bayesian tool Genie. These configurations include a mapping between different states and each node of the dependency model to be able to start learning parameters. Here we're showing how the conditional probability of transitions from each event to the critical event can be calculated using Bayesian theorem. At the end, each node in the model contains probability of all transitions. After initialization phase, LeaPS will be ready to intercept and verify each operation in the cloud in near real time. To show this, we provide a sample sequence of operations. The security property we're focusing on in our demo is no downgrade of security group for a running VM. This is important since changing security group from no connection to essential, which is a less restricted security group, will allow more connections to the VM and its security level will be downgraded. Therefore, we need to detect such breaches leading to compliance violation. Here, the cloud user is creating a VM, attaching security group no connection to it, and starts the VM. At that point, the attacker tries to downgrade the security property, which is detected as a critical event by LeaPS middleware and is blocked as it violates the security policy. Now let's see this in more details. Here, the first intercepted operation is creating LeaPS VM. LeaPS middleware intercepts the request and inspects the request body. Here we're showing the integration of LeaPS middleware in OpenStack Nova service. We can see the definition of the filter and its insertion in Nova pipeline. Therefore, every request made to Nova must pass through our middleware LeaPS first. Here, we're showing the mapping of each operation to the dependency model. LeaPS middleware inspects the parameters of requests and pre-processes the related watchlist of the monitored security property. Then it verifies the current operation and decides whether it violates the security property. Here we see the ID of the newly created VM. The cloud user is attaching the most restricted security group, no connection, to the VM. At this point, the VM is started by the user. The body of the request can be inspected by our middleware. Also, the inspected request body can be logged through our LeaPS middleware in Nova log files. Here we see that the related watchlist to the security property no downgrade of security group has been pre-processed. Expectedly, for LeaPS VM being attached to no connection security group, the only allowed security group is no connection, since this is the most restricted security group. Finally, at this point, the attacker is trying to downgrade the security group. However, as the body of the request could be inspected by the middleware, it could verify the operation and decides that it violates the policy. So it denies the request and there will be no violation according to security policy network isolation. Now let's see the results of proactive auditing in our ARC dashboard. In this donut chart, we can see a comparison between the number of allowed and blocked requests. In this bar graph, we're showing the number of block requests for different operations. For example, attach security group, create VM, or port update. Also, the last intercepted request has been highlighted in our dependency model. And we see it among the last 5 intercepted requests that are predicted as violation in this table. Here, we're showing intercepted requests in more details. Red lines are related to those operations predicted as violation and being blocked, whereas green lines are about those critical events that were not violating security policy and therefore have been allowed by LeaPS. Orange lines are those operations predicted as violation but have been allowed since the imposed proactive action has been chosen to be a warning for them by the ARC user. Here we're showing the sequence of operations on our dependency model. Other details of the request can also be intercepted by our middleware. As we can see, since the requested resource is more restricted than the allowed one, the request has been denied by LeaPS. Now let's look at the summary of what we have seen. At first, the VM is created by the user. Secondly, the most restricted security group is being attached to the VM. Then it is started by the user. At this point, the attacker is trying to downgrade the security property. However, LeaPS can predict the violation and denies the request. Therefore, there will be no violation according to our focused security policy, network isolation.